In this last video for the course from Chapter 9, we're going to learn how to solve systems of differential equations. So a system might be this: x of t equals 2x of t, or x prime of t, excuse me, equals 2x of t minus 3y of t, and y prime of t equals x of t minus 2y of t, and we're trying to find what x of t and y of t are given that pair of equations. Well, another way to write that pair or system of equations is by writing the left-hand side as a vector or a matrix, a column matrix, where x prime and y prime are the entries, and to get the right hand side of the equations, if we write this coefficient matrix 2 minus 3, 1 minus 2, and we multiply that by x of t in this position and y of t in this position, this column matrix here, then by the rules of matrix multiplication, it's 2 times the x of t plus minus 3 times the y of t, which gives this here. And then for the second row, we go 1 times the x of t minus 2 times the y of t, which gives this row here. So again, let's go through that again in case you've never done matrix multiplication. It's 2 times x of t plus minus 3 times y of t, and that gives this equation here. And then for the second row, it is 1 times x of t plus minus 2 times y of t, which gives this. In a more abstract setting, we write, or in a more generalized setting, we write this matrix as in a vector form: x prime of t as a vector equals this matrix of coefficients on the right, a, and the x of t, y of t we write as a vector, x. Or in shorthand form, x prime equals ax. What kind of a function x would be such that when you take its derivative, it's just a constant times x, as before when we were solving constant coefficient systems and the matrix A has constant coefficients? We use the exponential function because its derivative is itself except multiplied by a constant. So if we take the derivative of x of t, the r comes down, we get r e to the rt. We substitute that back into our differential equation. So left-hand side is r e to the rt, and the right-hand side is a e to the rt. Well, if we rewrite that by subtracting the left side, that's r e to the rt minus a e to the rt equals 0. If we factor out the e to the rt, we get this. E to the rt is factored out. Excuse me, we want to move this r e to the rt to the right side by subtracting it. So we have this form next, and then we're going to factor out e to the rt, and that leaves, you would think it should be a minus r, but r is a constant and a is a matrix, and so the way we make that work so that a is going to have a matrix of the same size subtracted from it is r times I. So let's see what that means off to the side here. So if A is a matrix of constants A, B, C, D, I stands for the identity matrix, which means that, or the multiplicative identity, it's a matrix such that when you multiply it by any other matrix, it results in the same thing. Notice, let's just, we can see this A, B, C, D times 1, 0, 0, 1. So it's, if we multiply this times this, we just get A. If we multiply this times this, we get B. If we multiply this times this, we get C. And if we multiply this times this, we get D. So it is the identity matrix, or at least that's confirmation of it. So when we say A minus Ri, that Ri is R multiplied by the matrix I, and it just changes those entries that are 1s to R's, so that one becomes a R, that one becomes a R, but these two are 0, so 0 times R is 0, and so it's A, B, C, D minus that, and so it actually looks like this, right? A minus R, B, C, those two entries don't change, and then the D has R subtracted from it. So that's what A minus Ri looks like in the general sense, and you can see that A minus Ri is a matrix, whereas if we just did A minus R, we wouldn't know where to subtract the R's. So we have this matrix system that we're trying to solve, and since we have on the left side the product of two things equals 0, we can see what happens when we divide through by B, which is the same as dividing through by this e to the RT. Well, actually I shouldn't say that, right? When we have a product of two equations equals 0, we have either A equals 0 or B equals 0 or both, but in this case the B part e to the RT, if we set that equal to 0, it's not going to have any solutions because exponential functions never equal 0. And I actually left out something here. The x of t, that's our assumed solution, it can't just be e to the RT, because remember that x of t, this right here, had an entry in two positions, so x of t needs to be a vector, so we multiply it by a vector u. So x prime is also multiplied by that vector u, and so there needs to be a vector u here, and here, and here. So we put the vector in u everywhere, but we still are dividing through by e to the RT, and when we do that, we're left with this matrix equation, A minus Ri, that's the matrix, times the vector u equals 0. Well, if you'd study, if one studies the theory of linear algebra, it turns out that this matrix system here has a solution only when the determinant of A minus Ri equals 0. So if we write that out, the determinant of A minus Ri, which is written like an absolute value, the determinant's written like the absolute value symbol. So what we need to do to solve this differential equation is take A minus Ri, that determinant, and set it equal to 0. So when we do that, that gives us what is called the characteristic equation of the system, just like when we solve for R in in earlier cases, we were finding the characteristic equation of the system. So let's see what the characteristic equation of the system looks like in this case. But let's first note that when we find the roots of R, so if we're going to do 2 by 2 systems, we're going to get roots of that characteristic equation R1 and R2, and then the solution of the differential equation will look like this. It will look like e to the R1t plus e to the R2t. That looks familiar, and there will be a constant C1 here and a constant C2 here, so you're at this point thinking that it looks exactly like what we got before when we found the characteristic equation at 2 solutions, but we also need to put in here this a vector because the solutions are vectors. So there's a vector u1 here and a vector u2 here, and these vectors and these r1 and r2 have specific names. So the r1 and the r2 that we find from the characteristic equation, they are called the eigenvalues. E-I-G-E-N. And these vectors u1 and u2, which we'll need to find, they take actually a little bit more work than finding the characteristic roots r1 and r2. Those are called the eigenvectors. So when we solve a system, we need to find eigenvalues and eigenvectors. So let's see how to do that, both of those on the next blackboard. So here is our matrix system, and we need to find where the determinant a minus ri equals 0. We said that when a minus ri, we subtract a down the main or r from the entries in the main diagonal. So this would be 2 minus r and minus 2 minus r, but these entries, the minus 3 here and the 1 here, do not change. And then we need to find the determinant of that matrix and set it equal to 0. Well, the way we find a determinant of a 2 by 2 matrix, we saw this before when we found Wronskians, is we take the product of these two entries added together minus the product of those two entries. So if we take the down diagonal, as we call it, positive, or the positive product of that, that's 2 minus r, and the other entry is minus 2 minus r. But if we factor a minus 1 out of that, that's 2 plus r, so there's the minus 1 factored out. And then this way we're subtracting, so it's minus minus 3 plus 3 equals 0. We collect terms. This entry here, or this product here, is 4 minus r squared. There's a negative sign out front, so it's r squared minus 4 and then plus 3 equals 0, or r squared equals 1, or r equals plus or minus 1. So those two solutions right there are called the eigenvalues, or are the eigenvalues. So we know that our solution, or we already know that our solution has this as part of its structure and this as part of its structure, and we're looking for those eigenvectors u1 and u2 that go here and here. So how do we find those eigenvectors? Finding the eigenvectors to do that, you're going to set A minus R I U vector equal to 0 for each R, which in our case is for R1 and for R2. This is just a little different than what we did before. Remember, before we were setting A minus Ri determinate equals 0. Now we're setting a vector equation equal to 0, and this entry right here, U, is the eigenvector. So we're trying to solve for that eigenvector. So let's see what that looks like on the next blackboard. So A, the matrix A minus Ri with R equals 1. So we have 2 and we subtract 1 here. We don't touch this 3. We put a 1 here. And this is minus 2 minus R. Right? So in these two, which I did that wrong, and this position is minus 1 also. So note that in these positions right here, we're subtracting the known eigenvector 1, and then we're multiplying that by the eigenvector U, and that U has two entries, which we'll call U1 and U2. We set that equal to 0, but 0 as a matrix, so 0, 0. So if we multiply this out, this entry is 1, this entry is minus 3, so simplified it's 1 minus 3, 1 minus 3, U1, U2 equals 0, 0. That gives rise to two equations, but it turns out that those two equations are the same. So if we take the first row times the first column, we get U1 minus 3U2 is 0. If we take the second row times that column, we get the same thing, U1 minus 3U2 is 0. And that will be the case when we have a pair of real eigenvalues. So we've got these two equations, they're both the same. We solve them and we find that U equals, or U1 equals 3U2. So our eigenvector has this form, U1, U2, and we found that what U1 is 3U2. So if we put 3U2 in for U1 and U2 in for U2, we don't change it, and we factor U2 out of there, we find that this entry is a 3 and this entry is a 1, and that relationship between the entries is called is the eigenvector. So 3, 1 is that first eigenvector. So if we go back to this form where we had our solution, we can write in that this U1 right here is the eigenvector 3, 1. And now we need to find this eigenvector U2. So now we're subtracting minus 1 from the entries here and here, and we're leaving these two entries alone, and we're solving for U1 and U2, we're actually finding the relationship between U1 and U2, and that gives us the eigenvector. So if we simplify this matrix, it's what, 3 minus 3 and 1 minus 1 times U1, U2, the eigenvector we're trying to find, we see that we get two equations that are the same, even though they're a little bit disguised. 3u1 minus 3u2 is 0, and u1 minus u2 equals 0. And that's the same as u1 equals u2. So in this case, the relationship between the entries is that u1 and u2 are the same. So if we write the eigenvector out, the u1, u2 turns into u1, u1, because the entries are the same. u1 equals u2, we factor out the u1, and we get this second eigenvector is just 1, 1. And so we go back to the form of our solution, take this eigenvector u2, and we write in the fact that we know that this is 1, 1 now. So here's the solution to the differential equation. Sometimes we write that a little bit differently by multiplying it out. We should say this is x of t equals that, right? But x of t is a vector. So if we multiply this out, right, bring this constant into this vector, what do we get? We get 3c1 3c1 e to the t, but add to that is what, c2 from over here, c2 e to the minus t, that's in the top position in our vector solution, and then in the bottom position it's what, c1 e to the t times 1, so c1 e to the t plus c2 e to the t in that position, so plus c2 e to the t. And so if we write our solution x of t in that form, that's sometimes the more common form where you see what the vector actually is, where you see the solution in vector form as opposed to in this form here. So we solved a differential system, actually this differential system right here, and it was pretty different, or the same in some ways, finding the characteristic equation and it having two solutions because it was a quadratic, and having exponentials involving those two solutions as the R1 and R2 as powers of the exponential. That was the same, but the eigenvalue part of it is different. Now we want to, so this is one type of system of differential equation, or I mean, this is a 2x2 system. There are other types of 2x2 systems where the eigenvalues are complex, and we want to look at that in another video. So this will conclude this first video on solving systems of differential equations. So let's call this video number 1.